So today I want to talk about what we're looking forward to in sunspot cycle 25, the flare observations and models, what we've been doing to prepare for the flares that will start to happen much more frequently very soon. So we're in particular looking forward to data from the DKIS, to the Daniel K. Inouye Solar Telescope, which is a new solar telescope on Haleakala in Maui. It's a 4-meter solar telescope, so it's the biggest in the world. And it's hopefully going to provide many exciting new flare observations for us, so that we can address some really interesting long-standing problems in flare physics, and some new problems that were revealed over last solar maximum. The problem I'm going to focus on today is what I'll refer to as the large beam flux problem, how to explain these large heating rates in solar flares. We've been doing a lot of work comparing to observations with IRIS and bringing our models up to speed, so we'll be ready to interpret the observations from the DKIST when they start coming in. In fact, they have started coming in, and I'll show some at the very end. And then at the very end, I'll switch topics a little bit and transition to stellar flares and discuss the solar-stellar connection, how we can learn from each other. So back up a little bit and talk about the solar atmosphere. Before a flare, the corona is very hot at millions of degrees. There's a transition region and a denser chromosphere. Temperatures around 6,000 degrees, temperature minimum region in the photosphere where the visible light originates from. During the flare, almost everything becomes a lot hotter and a lot denser. So the flare corona can reach temperatures of tens of millions of degrees, and the flare transition region moves to a deeper region of the atmosphere, a denser region, lower altitude. The chromosphere becomes hotter and denser and shifts towards the solar surface as well. We can attribute the flare corona to the really spectacular images of flare loops that light up very brilliantly in the later phases of a flare typically. So here's a well-studied flare on the limb, and then a different flare looking face down shows you the H-alpha line, what you see when you observe at lines that are sensitive to lower temperatures. You see the heated chromosphere. And we can attribute the chromospheric flare to structures what we call flare ribbons. So this is a 2-ribbon solar flare with 1 ribbon occurring here and another ribbon occurring here. And along these ribbons, there are regions of more intense brightenings, what we call kernels. So there's a lot of jargon we use in solar physics, and especially in flares, and I just wanted to introduce you to a little bit of the jargon here. These 2-ribbon solar flares occur around sunspots, but not just any old sunspots. These sunspots here, they're not nice and symmetric and circular, but they're all jumbled up and interacting and merging, and new sunspots are forming all the while. So zooming out, I wanted to show a movie of an H-alpha solar flare from 2014. So the flare will happen around here, and then I will zoom in on it, and you'll see the 2 ribbons that form. You can't see it in here, but there's a sunspot. There are a couple of different sunspots, and they're very close together and interacting with each other. You might even be able to see a blast wave that emanates from the flare, which affects a large fraction of the solar disk. I'll let it play one more time so maybe you can catch it. It is right there. So it goes up that way. It's called the Morton wave. So flares occur as localized brightenings around sunspots, but they can have global effects on the sun. And they can also affect our society here on Earth by ionizing layers of the atmosphere, causing disruptions in radio communications. My talk today is going to be mostly on the optical and near ultraviolet aspects of solar flares and stellar flares, but flares produce emissions from the gamma rays to the radio. Flares are just one part of a larger event called the solar eruptive event, or SEE. The SEE is composed also of mass and magnetic field that's ejected from the flare area, and this is the coronal mass ejection. And in fact, most of the energy is in the kinetic energy of the coronal mass ejection. Of the remaining 20% in the flare, most of the flare energy is in the near ultraviolet and continuum radiation. It's what's collectively called sometimes the white light, some more jargon there. And very little is actually in the emission lines and the X-rays, which are important for the ionospheric effects. Particles are accelerated at the CME and can reach the Earth ahead of the CME. These are the solar energetic particles, and they can be impulsive or gradual and last for days. So the sun goes through magnetic activity cycles every 11 years. It produces a large number of sunspots and therefore a large number of flares. Last solar maximum, which occurred between 2012 and 2015, was relatively tame compared to the previous solar maxima. Here I show up-to-date plot of the sunspot number over the last several solar maxima. And it's an important question to at least get a grasp on, is how active the sun will be over the next solar maximum, solar max 25, which will peak around 2025. We're already starting to see a lot of flare activity, and it may be more active than the original prediction by NOAA and NASA. So NOAA and NASA originally predicted it to be one of the most tame solar maxima in recorded history. And then a new technique was published, which is a more empirical technique of predicting the next solar maximum. And it predicted the solar max 25 to be one of the strongest on record. So we have these two widely disparate predictions, and they're continuously tracking how they compare. I show in the bottom panel here. We'll just have to see who is right, NASA or the empiricists at HAO. Either way, we're going to learn a lot about the solar magnetic activity cycle and predicting further maxima. Unfortunately, our daily lives are still susceptible to an extreme event on the sun. And the worst case scenario is still that certain regions of the globe or country can lose power for a very long period of time. And we really, really don't want to be alarmist about these types of things. So we're really measured, but the threat is still there. And Bill Nye actually talks about this in his third episode of The End of the World is Nigh, goes through the worst case scenario. Fortunately, the government is aware of these threats and is apparently acting on them. So for today, we can just sit back and enjoy the physics and observations of solar flares. I always like to show an image of the sun from the most current time, from the Solar Dynamics Observatory. This is in visible light. You can see there are a couple of sunspots here in the north and southern hemispheres. And then on the right is the X-ray monitoring. This is how we classify flares according to the peak flux and the soft X-rays, the green curve here. So over the last couple of days, there was apparently not much going on. Maybe a C flare. The biggest flares that will occur will be X10 or X20 next cycle, so way up here. But there was apparently nothing going on. Yet there was some spectacular aurora over the past day or so. And people are still trying to figure out what caused this. Was it a glancing coronal mass ejection that put a crack in our magnetic field and allowed the solar wind to seep in? That's one of the working hypotheses, but the sun can still very much surprise us. We were not expecting that in the associated geomagnetic storm. So we have a good idea of where the solar flares occur, not just any old sunspot that are nice and circular and mostly symmetric like these, but with the magnetic field information from the Solar Dynamics Observatory, we can get a much better grasp of where these larger events will occur. And they'll occur where there's a sharp transition between the northern polarity and the southern polarity of the magnetic field. If I were to guess, the C-class flare probably happened right here, where there was this sharp transition. There are mixed magnetic polarities around this sharp transition, which are the ingredients for a flare. It's kind of like predicting tornadoes. You know when the conditions are right. You just don't know like where exactly it's going to occur in the region and how strong it's going to be and when. So I'd argue we actually have a better idea, but don't tell the meteorologists that. So we've learned a lot about solar flares from the observations over the last solar maximum, thanks primarily to the IRIS mission, which is a NASA satellite observatory that observes the sun in the near ultraviolet and far ultraviolet. It obtains spectra and images around carbon-2 and silicon-4 in the far ultraviolet, and the near ultraviolet around the magnesium-2 resonance lines. It originally wasn't a flare mission, but it has provided many incredible flare observations for us. It has become very efficient at predicting where the flares occur and placing the spectrograph slit right over where the flare ribbons light up. So I'm going to show a movie of one of the first X-class flares of this solar maximum from last March. On the left is going to be a movie of the silicon-4 line, which is sensitive to around like 80,000 K. And you're going to see both the ribbons and foot points closer to the solar surface light up. And then later in the flare, you'll see the loops light up. So I'll play it here. So we have the two ribbons, and you can see that they apparently spread apart from each other. That's a common phenomenon in these large solar flares. And then later on, you also see the loops that connect the conjugate ribbons light up with plasma there. So at higher temperatures, like in the X-rays, you predominantly see the loops, and lower temperatures like H alpha and the optical continuum, you predominantly see the ribbons and the foot points, the kernels. On the right, I'm going to show the spectra along the slit. So the spectrograph slit is actually right here. If you can see my mouse, it's right in the center. And so we have spectra at every spatial position. And on the right, I'm going to show the near ultraviolet spectra around the magnesium-2 resonance lines. You'll be able to see, I want you to notice a few things. First, the dramatic increase in the brightness of the emission lines, but also a broadband continuum increase. And then finally, in the emission lines, you'll see these really striking redshifts. So every position here vertically corresponds to a different spatial location on the slit. So there's the flare ribbons. You can see the really incredible redshifts that form in the broadband continuum response. This is magnesium-2K and magnesium-2H. All right, I'll let it play one more time. And you also can notice that the apparent motion downward, just like in the movie on the left. So we have all this incredible detail. We have these very broad and bright and redshifted emission lines. This is what we want to understand with flare models. I do want to take a step back and talk about where we think all this energy originates. We think it originates in the corona through twisted, tangled, and stressed magnetic fields around these sunspots. And through the process of magnetic reconnection, the energy in the magnetic field is released into the atmosphere. There is a very important next step before you see the flare, and that is the transfer of magnetic energy into particle energy. So acceleration of electrons and protons and ions out of the thermal distribution of the corona and into beams, so power law distributions. There's been a lot of really exciting MHD work on the reconnection and energy conversion process on the sun, I show in the center panel. And what they're finding is where you have the reconnection region here, there are plasmoids that form, which are localized regions of magnetic connectivity, illustrated as the ovals in the bottom middle cartoon, which start very elongated, but then relax to a more circular shape. And in this process, is generally thought that ambient electrons are accelerated through Fermi reflection. And this could be one of the main sources of energetic particles that stream into the lower atmosphere in the flare. Simulations of reconnection in other astrophysical scenarios are also showing these plasmoid structures. On the left is a simulation of a neutron star magnetosphere, where the plasmoids are these little knots here in the reconnection region, or in the neutron star. And on the right is a simulation of an accretion disk around a supermassive black hole, where they zoom and point to specific plasmoids. So plasmoids may be ubiquitous across many different areas of astrophysics. And in the sun, we can understand them in great detail. We've seen these in simulations for many years, and many such wonderful cartoons have been illustrated in the bottom panel here, showing the action of plasmoids. However, plasmoids are possibly not the only source of energetic particles. It's currently a very hot debate about where these electron beams actually originate and through what acceleration mechanism or series of mechanisms. On the right, I show a series of flare loops on the limb of the sun, and the background image is the thermal emission, and the contours show the non-thermal hard X-rays. So we have non-thermal hard X-rays in the corona, and at the foot points where the ribbons are, and it's where you have these that the energetic electron beams are interacting with the atmosphere, producing Bremsstrahlung radiation. So the reconnection region presumably happens up here, and then you have a turbulent outflow. And in this turbulent outflow, you may also have a lot of stochastic acceleration and resonant acceleration. So it's currently, we're trying to understand where these electrons are coming from, how they're produced. Recently, we've learned that these electron beams are extremely dense, much denser than we've assumed in the decades past. So the sun is a very, very efficient particle accelerator. This is something we've only come to realize over the past about 10 years, that almost the entire thermal distribution is being accelerated into the beams. Recent observations from radio have also been consistent with this idea. So the beams are produced presumably in the corona somehow, and they spiral through the magnetic fields and slam into the lower atmosphere, losing their energy via Coulomb collisions, heating the chromosphere, causing an explosion in the foot points. So we have these very energetic electron beams in the corona. What happens when we look closer at the chromosphere? Do we also see evidence of such intense electron beams penetrating and lighting up the atmosphere? Thanks to higher spatial resolution data of the chromosphere, we have come to realize that these beams are focused in very, very small regions in these bright kernels along the ribbons. So on the right, I show, or in the middle, I should say, I show in contours the hard X-ray non-thermal Bremsstrahlung radiation from the beams scattering off protons in the chromosphere, and then which is a non-thermal process. And then the image on the left is the thermal response due to the energy loss through Coulomb collisions with the electrons in the chromosphere. And so you can take the total power in the non-thermal electrons that are producing the Bremsstrahlung, and you divide by the high spatial resolution areas, and you get an energy flux. And this is a really important parameter for connecting the coronal energy release to the response of the lower atmosphere. So what they got were energy fluxes of 10 to the 12 to 10 to the 13 ergs per second per square centimeter, impacting the chromosphere in these bright kernels in the ribbons. I'm going to refer to these as F12 and F13 respectively. The electron beams have a power law distribution. They have a certain minimum energy, a low energy cutoff, about 20 keV, and the energies extend up to hundreds of keV to MeV. Okay. So with other recent observations, you can also convince yourself of such large fluxes, 3.5, F11, 2 F11. These are much larger than what have been inferred in the past decades, and it's primarily due to the higher spatial resolution of these brightenings. Why is this interesting? Why is this potentially a problem? Well, if you have high flux electron beams that are produced in the corona near the acceleration region, the electron beams will stream ahead of the accelerated protons. You'll get a very, very strong electric field that forms because of the charge displacement. And this electric field will actually act to slow down the beam itself. It will drive a background current, and that current will deposit the energy of the beam into the plasma. So what will happen is the electron beam will stop over a very short distance. It won't even reach the chromosphere if you have such large beam densities. And so what you'll have is a thermal flare, and the energy will be conducted into the chromosphere, and you'll see purely thermal X-rays in the foot points instead of non-thermal foot points, which is what are actually seen here. So how do you get these huge beams down to the chromosphere is a really important question, and is how my group critically examines flare models by comparing to spectra of the foot points and testing the predictions of electron beam models. There's also these beam instabilities, which I won't go into, but those act even more drastically to stifle the beam where it's even formed and deposit the energy in situ. So before I talk about the models that we do use to understand the impact of high flux electron beams in the chromosphere, I want to briefly discuss where we'd like to be in 5 or 10 years. So maybe there's more of an appreciation of the steps that need to be taken in modeling advancements. So on the left, I show a 2D model of a flux tube, which expands from the photosphere out into the chromosphere and the corona. Okay, this calculation is provided by Han Otbrick. And so we'd like a multidimensional multidimensional model in space. This is a static model, and so we need to add in very extreme hydrodynamic processes, shock phenomena, and radiation transport on uneven grids. And so we need a lot of sophistication to this to model the explosion in the chromosphere. And for this, I think the best path is something in the bottom where we have a implicit 2D adaptive grid that's from Stokel and Dorfy. But these two have not been merged together, and so we don't have such a capability yet to model the shock phenomena in multiple dimensions on the scales that are important for flares. But what we do have is a code that has been modified over several decades to study flares. It was originally developed to study the quiet sun and the acoustic shocks that form in the quiet sun outside of active regions. This code is called Radian. It is a 1D code, meaning it's, we assume field aligned flows plane parallel rate of transfer. It has many non-equilibrium processes in it, which are really important for flares, like shocks. It has a sophisticated adaptive grid to resolve sharp gradients in the pressure and temperature and velocity. Importantly, it solves the system of equations through implicit Newton-Raphson, and therefore we're not limited by the Courant time step, which is extremely tiny in the flare transition region. We model the photosphere, chromosphere transition region in corona self-consistently with radiative transfer calculated. To simulate the flare, we take an electron beam and we inject it into the top of the flare loop. So we don't actually simulate particle acceleration or reconnection. We assume that particle beams are produced, and therefore we can, change the different parameters of these particle beams. Then we use the Fokker-Planck equation to solve for the heating rate over the atmosphere. And this Fokker-Planck equation has gone through a lot of development and has a lot of knobs and switches with really interesting physical processes such as magnetic mirroring. But today I'm just going to show the response due to the Coulomb energy loss of these electron beams. And I'll show you a movie on the right here of a high flux electron beam simulation. In the top panel, I have the temperature in black, the temperature evolution. You'll see that the flare transition region moves deeper and deeper and deeper. And the beam heating is in red, which will happen over a pretty narrow region. But it contributes to heating over almost the entire atmosphere. In the bottom panel, I just want you to pay attention to the gas density, which is the green. Before the flare, it's an exponential, but in the flare, you'll see very interesting changes in the gas density. So I'll loop this here. And this occurs over about 10 seconds. Little play there. So you can see the flare transition region move closer and closer to the photosphere. And what happens below this flare transition region is the sharp thermal pressure gradients cause a pileup of mass below the transition region. And that manifests as this increase in gas density right here. This is fully resolved and is only about 25 kilometers. It starts very hot at about 100,000 K, and then this high density plug cools and cools and cools as it radiates away energy through the detailed transitions. And this is what we call a chromospheric condensation, this high density plug. It's our working hypothesis that these large electron beam fluxes generate these chromospheric condensations, which then generate the bulk of the observational signatures we see from the near ultraviolet into the optical. For example, those redshifted components in the magnesium-2 lines from IRIS. So how do the spectral predictions from a model like this compare to IRIS observations? Well, I'm going to focus on some iron-2 emission line observations instead of the magnesium-2. I'll come back to the magnesium-2 in a little bit. So here are some comparisons of that model, in fact, to observed iron-2 line during an X-class solar flare in 2014. This is a very well-studied solar flare, and we're still trying to understand many aspects of this flare. So there are many iron-2 emission lines in the flare, and they are much more optically thin than the magnesium-2 lines, and we can see deeper into the atmosphere. So that's why we look at these iron-2 lines. The observation is the black histogram in the top. We see an emission component around the rest wavelength here, and then we see a broadened redshifted component in the iron-2 right here. This here is an iron-1 line, which shows similar features. Put in our model, shown as the colored lines, just have the iron-2. First, we produce a emission component around the rest wavelength, and then a redshifted component appears and becomes brighter and less redshifted over time. So at first glance, this is not too close to the observations, but we can average over the model in clever ways over 8-second exposure times and we get better comparisons to the observations. So in the bottom panel shows different temporal averages, showing that in general, the brightness of the red wing component and the redshift is consistent with the observations in this particular flare. I just want to point out that we haven't scaled our model in any way. We just put the model spectrum right onto the observations, and the overall continuum increase is pretty well matched, as well as these two really interesting line components. Oh. So what is going on? Well, we can go into the model and figure out where these two emission line components are being formed. Here's a cartoon that summarizes the response of an atmosphere to a large electron beam flux into the chromosphere. So the electron beams stream down, they heat the chromosphere to millions of degrees, causing an explosion. And you have, as a result, mass motion up into the loops, and you have mass motion down, the lower chromosphere being compressed into this chromospheric condensation. All the while, the electron beams are supplying energy to the condensation and also to the layers below the condensation these layers are being swept up by the condensation. They're not really, they don't have any significant velocities, and so we refer to them as stationary flow layers. And what we find is that the emission around the rest wavelength of the iron 2 line originates from the stationary flare layers and is able to escape. And the redshifted component is originating from the condensation. And the evolution of the redshifted component is tied to the temperature and density evolution of this condensation. But then come along better observations of a different solar flare with higher time resolution. This observation had spectra every 9.5 seconds. And here I show a sequence around that iron 2 line. So this is total about 45 to 50 seconds. You see first the emission pops up around the rest wavelength, and then about 10 seconds later, you see the redshifted component become very prominent and very broad. It eventually reaches the same intensity as the emission around the rest wavelength and becomes less and less redshifted. Without the time resolution, we wouldn't have known how to interpret this last spectrum here. We probably would have said this is one emission line that has this very faint red tail that we don't really care about. But in fact, we have to care about it because the line is actually a superposition of two different components. These other lines, this is an iron 2 line, this is an iron 1 line showing the same behavior. So every flare has its own personality. I'm going to skip over that. Every flare has its own personality, and we can run a simulation for this particular flare using the electron beam parameters that we infer from the hard X-rays for this particular flare. The electron beam flux is not quite as high, but it still results in similar properties in the emission line. We see a redshifted component that pops up, gets brighter and less redshifted over time. We can compare this to the high time resolution data. We find some pretty striking discrepancies. First, the redshifted component is much brighter than the emission around the rest wavelength. That's a really important discrepancy. Second is the time scale of the model. This evolution of the model takes place over about 15 to 20 seconds, whereas the evolution in the observations takes place over about 50 seconds. So we have a factor of about 2 to 3 error in the time scale. And third is the broadening of the line. So the redshifted component extends all the way out to 2815 angstroms and is very broad, whereas in the model, it only goes out to 8.9, okay? So we've done some quantitative comparisons and we're seriously lacking in the broadening of this emission line and in other flare models. So in summary, we have these 3 discrepancies. The evolution of the model is too rapid. the red wing component to the emission line is too bright, and the red wing component and the emission around the stationary, around the rest wavelength also, it's just too narrow, not enough broadening in the emission line. So I want to first touch on the third point here. And in doing so, we'll turn my attention to the magnesium 2 lines, which were just a few angstroms away from those iron 2 lines. The magnesium 2 lines are the resonance lines, so they're very optically thick. So discrepancies in broadening in the wings will show up to a much greater degree in these more optically thick lines. So just think of the curve of growth effect. So a student who worked with me, Yingji Zhu, looked at a different X-class flare and found these really interesting flare spectra. The magnesium 2 K and H lines are very broad in the wings. And Yingji looked at the current prescriptions for the collisional broadening in these radiative transfer codes that we use. And he found that the theory of the collisional broadening for magnesium 2 and other non-hydrogen lines needed to be updated from the 1940s theory to the 1960s theory. And that is the difference that is shown from the orange to the red lines here. So clearly important, but not enough to explain these really, really impressive wings in the magnesium 2 lines in the flare. So then Yingji got creative and multiplied the collisional broadening damping in these magnesium 2 lines by a factor of 30, just to see what we get. And that's shown in the bottom panel. We can see that the ad hoc increase in the damping leads to these really impressive Lorentzian wings that are much better in agreement with the overall properties of the broadening. Additionally, the more minor magnesium 2 lines here are also consistent. So we have more optically thin and very optically thick lines being now pretty well reproduced, but we still have no idea what would cause such a discrepancy in this broadening. So we can look at alternative hypotheses to the broadening. We can play with the microturbulence parameter, which is just an ad hoc increase in the Doppler broadening component to the line, perhaps representative of gas turbulence of some sort that's not in the models, not in the 1D models. And so Yingji experimented with several different prescriptions for microturbulence and found really, really bizarre looking line profiles. If he fine-tuned the microturbulence such that it's even supersonic, we still don't get the really, really nice damping Lorentzian wings in the observations. And also the magnesium 2, more minor magnesium 2 lines are just completely off. All right, so we have a pretty incredible mystery on our hands. What are we missing from our models? Is it deep heating in the low chromosphere where the wings are formed? Is it something to do with the interaction of the beam with the magnesium 2? So that's an unknown problem, but we can start to address some of the other glaring discrepancies and motivate new observations, in particular, the brightness of this red wing component to the emission line in iron 2. The question we ask is, are the monochromospheric condensations in our radian models too dense? For example, because the flows can only go in one direction, up or down, they're confined, and so you have a accretion of too much mass in a too small vertical area. And to answer this question, we need to look at lines that are well understood in terms of their broadening sensitivity to the density, and lines that broaden dramatically to increases in the density. And these lines are the hydrogen lines, which broaden dramatically due to the Stark effect. So in the flare chromosphere, there is some neutral hydrogen, it's partially ionized. You have some ambient electrons, you have some ambient protons. These are not the beam electrons, by the way. These are just the ambient electrons and protons. And they perturb hydrogen atoms and break the degeneracy in L in each principal quantum number, illustrated on the left. As the electric field magnitude increases, the splitting of the hydrogen line increases, and you have much larger splitting for the high order transitions. For example, 14 to 2 would be brought in much more than 5 to 2 for a given field strength. So how do we know this is even important in solar and stellar flares? Well, the evidence comes from looking at the stars. On the right, I show two different observations of two different M dwarfs during two very different flares in terms of their energies. And what we see is that the hydrogen-Balmer epsilon line broadens dramatically, whereas the calcium-2 resonance lines, like the magnesium-2 resonance lines, don't broaden as much, nearly as much. And so this is evidence that pressure broadening is really important in generating these wings of the hydrogen lines. And from the pressure broadening, we can get an estimate of the electron density in the flare chromosphere. So just a little bit of overview of the pressure broadening of hydrogen lines. It's actually a really complicated plasma physics and quantum mechanics problem. Why is that? Well, because the ambient protons and ambient electrons, they're flying around at different speeds, and they broaden the hydrogen lines in different ways. The protons are slow, and they cause the splitting of the hydrogen line, of the principal quantum number, and generate what's called a Holtzmark profile. The electrons, however, are very fast, and they'll cause an accumulation of phase shifts, what we call impact damping, generating a Lorentzian profile. Moreover, the electrons can also cause transitions among the Stark split states of the atom. We say the broadening is non-adiabatic, and so full quantum calculations are necessary. Electrons further are really, really difficult because they don't just generate impact broadening, they also have a quasi-static component way out into the far wings. So there are a couple of theories that have been developed over many decades that self-consistently treat the electrons and protons. The one I'll talk about today is the unified theory, which was developed in the 70s, but is the current state-of-the-art theory in white dwarf atmospheres, Tremblay and Bergeron, 2009. So it's been a question of, for a long time, of how to include an accurate prescription of the broadening of hydrogen lines and solar and stellar flare models. Various approximations have been made, and none of them are sufficient. Here I just show a comparison of the various approximations for the H gamma line, which is 5 to 2. And the correct answer is this one here, which are the unified theory profiles, which are have been updated and included into white dwarf atmospheres. So how do our models of chromospheric condensations change from the old broadening prescriptions that we use, which weren't really justified, to the actual correct unified theory broadening? Here I show an H-alpha line prediction of a simulation to a large electron beam flux where the chromospheric condensation gets very dense. The new H-alpha line profile is the solid black line, which is much broader than the older prediction. We would really like observations in the wings to test these extreme broadening predictions. However, most solar instrumentation samples just around the line core of specific lines through Fabry-Perot imaging spectroscopy. I show one observation of an X-class flare from IBIS in the red here. The overall shape is remarkably well reproduced by our new prediction. However, I had to scale the observation by a factor of 7 in intensity, constant scale factor, perhaps to account for issues with spatial resolution in the data. There's always this issue of spatial resolution and getting an accurate value of the intensity. On the right, I show the H gamma line at various times in the simulation, up to 10 seconds. We have a emission component around the rest wavelength. And then as the chromospheric condensation cools and gets really dense, the entire line gets very broad and redshifted. So these wavelength windows are for the VISP, the visible spectral polarimeter, which is an instrument on the DKIST. And so that's what these predictions are for. I just want to mention really quick that we can analyze our models and figure out where the wings and the core are formed by analyzing the contribution function to the emergent intensity, which I show on the left. So we have height versus wavelength. Most of the line is formed in a very narrow layer in the chromospheric condensation, which is flowing downward and accruing more material. But the broadening here is not just due to the increased charge density in the chromosphere, the Stark effect. It's also due to optical depth effects, which enhances the broadening in these lines. We can look at the higher series members, which are expected to broaden more dramatically. And they're also more optically thin. So you won't have these opacity broadening or optical depth broadening effects. But when we look at the predictions for how the higher order Balmer lines merge into a pseudocontinuum, we find that actually they're narrower than the H gamma and H alpha line, and moreover, there is no redshift. So this is pretty surprising, but there is an explanation for this, and that is that the chromospheric condensation in this model is so dense that non-ideal effects come into play. That is, the upper levels of these transitions here are completely wiped out and dissolved due to non-ideal pressure ionization effects, so to speak. And so what you have is a translucent opacity window, and you're seeing deeper into the stationary flare layers, which are lower electron density, and therefore are giving you less broadening. We can compare to archival observations showing perhaps a reasonable agreement. We would, of course, like more observations of the low-order Balmer lines that are optically thick, like H alpha, H gamma, and farther into the wings, and we would like observations of the high series members. So what happens, though, when we get DKIST observations, and in the case that we find that our model chromospheric condensations are producing Balmer lines that are just way too broad? Do we have an alternative hypothesis? And in fact, recently, I proposed an alternative beam heating hypothesis. This is a different treatment of the electron beam transport in the corona. In particular, it comes from Kantar et al. 2012, who considered the time-dependent evolution of the electron beam in the corona, while also taking into account the evolution of background plasma waves, in particular, the Langmuir waves and ion acoustic plasma waves. In summary, what they found is that the electron beam first transfers energy to the background plasma waves, the Langmuir waves, which then interact with the ion acoustic waves. And then the Langmuir waves shift to lower values of angular wave number, higher phase velocity, and can resonantly accelerate the higher energy electrons in the beam. So you have a transfer from the beam to the plasma back to the beam at higher energy. So you have a lot more higher energy electrons, which can go deeper. I show two different predictions. The standard approach, which we've been using all along, is shown in green teal here. So you have the low corona, the transition region, the chromosphere, temperature minimum region, and photosphere. This is the standard approach, where the most beam heating is high in the chromosphere. And then with the Kantar et al. Beams, we have a maximum at a factor of about 100 larger column mass. Now, this is really important because if you heat this column mass to 10,000 K, you'll produce optically thin continuum emission. If you heat this column mass to 10,000 K, you'll produce optically thick continuum emission. You get very different emergent spectra. Unfortunately, we don't have all the data for solar flares that we'd like to compare to this new modeling approach, but we do have the data for stellar flares. We have broad wavelength coverage spectra of many, many stellar flares, allowing us to test this new alternative hypothesis to high flux electron beam transport. So that's the final part of my talk. I just want to discuss very briefly transition to stellar flare modeling. We have updated hydrogen broadening. We have this new electron beam transport mechanism. We include all this in our models, and we compare to several well-known large M dwarf flares. In particular, the super flare of 80 Leo from 1985, which has been used widely in the exoplanet habitability modeling community. This is a spectrum at the peak around the Balmer jump, where you have the Balmer emission lines and a Balmer jump, but a very, very impressive and luminous continuum between the lines. So we take one high flux electron beam and we simulate the response, and we get a model that well reproduces the shape of the continuum and the optical and the broadening of the emission lines. And then we take a lower flux electron beam and we attribute that to the Balmer jump and the rest of the emission and the lines that isn't so broad. We have sanity checks from the sun. We can look at the sun and see if the superposition of these two makes any sense to explain the full flare spectrum. In the sun, we see these bright kernels and then more diffuse ribbons over a larger area. And the ratio of areas that we need to explain the full flare spectrum, the total spectrum shown in blue, is coincidentally just the ratio of these two areas here. We can look in more detail at the comparisons, just to show you the H gamma line and the broadening of the high order series members, pretty well reproduced by this new modeling approach with our updated hydrogen broadening. However, statistically significant is not necessarily physically significant, and so we really need sanity checks from the sun. We need to place a spectrograph slit over these bright kernels and more diffuse ribbons and compare the broadening and continuum properties as a function of the position along the slit. We'd really like to then go to the M dwarf flare archive and apply this flare modeling approach. Here's an example of a different stellar flare with very high spectral resolution. This is the H gamma line. And this is just the kernel model with the heating very deep in the chromosphere. And you can see that we very well reproduce the continuum and the shape of the wings here. What's really exciting is maybe this going back to the sun and applying this modeling technique, the contour et al. Beam transport and the heating rates. I might be able to explain the discrepancy in the red wing component to the iron 2 lines, why it's too bright in our current models. If you put more energy deeper in the atmosphere and less in the condensation, then you might be able to have a better agreement with the observations. So we'd really like DCAS flare spectra for sanity checks on this superposition of several different spatial components. You know, the flare stars are spatially unresolved. That's a very heterogeneous flaring region. But with the sun, we can disentangle this heterogeneous flare source. Here's an image of a solar flare from Iris. I took Iris to the sun and I looked back at Hurricane Teddy, and this is what we saw. And then I took the VISP on the DKIST to the sun, and I observed Hurricane Teddy. And you can see that the spatial resolution is going to be really dramatically improved with the DKIST and the VISP. It's going to be really exciting to see what kind of substructure we're going to see to these little kernel brightenings. Of course, I have to show some first results from the VISP. The first flare that was observed, a student of mine is studying this. We have strategically placed a spectral window using the VISP around calcium-2H and H epsilon. We expect the H epsilon line to broaden dramatically due to the pressure broadening, Stark effect, and the calcium-2 line to be less broadened and maybe show these redshifts. So we can very clearly disentangle between electron density, optical depth broadening for the Balmer lines, and like maybe turbulent broadening for the calcium-2 lines. This was in the decay phase of a pretty small flare. We didn't catch the impulsive phase, but still it's going to be very, very interesting. So in summary, we have made some progress in 1D radiative hydrodynamic modeling and understanding the different sensitivity to the flare atmosphere for different hydrogen lines. The low order hydrogen lines, H alpha, are very optically thick and formed in the condensation entirely, whereas the high order Balmer lines are more optically thin, and you can see deeper into the atmosphere. We still have some severe problems in explaining the broadening of the resonance lines like magnesium-2 and the other non-hydrogen lines like iron-2. But with hydrogen, we have a really robust theory in our models and we'll be able to constrain the densities that are predicted in these downflowing regions. And finally, I really look forward to new multidimensional solar and stellar flare modeling approaches, perhaps with it will be necessary to have adaptive grids and radiative transfer and all the different physical aspects that I've talked about today. So thanks a lot for your time, and I guess I'll take questions.
Thanks, Adam. We have time for a couple of questions. Sean.
Hi, Adam. Awesome work. Thanks for the talk. Yeah, so you showed a lot of possible reasons for various discrepancies between the models and the data. And I was wondering, how much have you looked at, and how much do you think might be a factor that you're using 1D models and real electron beams might be kind of 1D because they're magnetically confined, but actually within the resolution element of your telescope, you have multiple 1D beams, each of which might have slightly different parameters like beam densities and such. So you have a superposition of multiple models.
Yep.
Is that important?
Yeah, so that is the approach we're taking for stellar flares. But for solar flares, that also could be a problem. And IRIS has great spatial resolution, but there is some evidence that it's still not resolving the details of these kernels. For example, if you look at the kernel here, you might be able to convince yourself of some substructure, the most intense brightenings are just like, a couple of pixels, and that's always very suspicious, right? When you just have like 2 pixels that are really bright, it's like, okay, probably something's unresolved there. And so, yes, indeed, that is something we're really looking forward to addressing with the better spatial resolution of the DKIST. It'll be about a factor of 10 better than IRIS, about a factor of 4 better than the best ground-based observatories today. So we will be able to place our slit, hopefully get lucky along these kernels, and better disentangle like the different heating rates that are contributing to different areas of this kernel.
Thank you.
I've got one. You said something that I enjoyed about each flare having its own distinct personality. I was wondering if you could say a little more about how different solar flares are different from each other and to what extent we understand that from models.
Great, that's a great question. I'll answer it for solar flares, and I'll briefly answer it for stellar flares because I think we have a better idea for stellar flares. But for solar flares, I don't have a plot here, but we've done the similar analyses of the iron-2 lines, of the magnesium-2 lines, of the continuum for several different X-class solar flares. And I had a PhD student who just graduated who did a statistical analysis of the red wing asymmetry, the red wing component in different solar flares. And oftentimes we'll see similar evolution to what I've shown, but in some cases, we'll see a very faint emission line and a really bright continuum increase. The emission line won't have such a prominent spectrally resolved redshifted component. So We don't understand this. We're trying to understand the different properties with models. For example, it could be that the electron beam energy just goes a lot deeper in some flares and produces more continuum compared to the emission line. In other flares, the electron beam gets entirely stopped in the chromosphere and produces these really bright emission lines with some amount of continuum, but the chromospheric condensation evolution will give you a lot of emission line intensity compared to the continuum. And so it could be the distribution of heating between the low chromosphere and the upper chromosphere, in short. In stellar flares, we know empirically that different flares have like pretty drastically different properties, in particular around the Balmer jump. So this flare here has a relatively small Balmer jump and relatively large optical continuum flux. And other flares that are more gradual in their evolution have a much larger Balmer jump and much fainter optical continuum. And this too could be due to the different amounts of heating in the upper chromosphere compared to the lower chromosphere. Also, because we have a heterogeneous flare source, maybe the ribbons are just much more dominant in the flares with larger Balmer jumps, and there are just fewer like really bright kernels. Whereas in this flare, there's there's a larger area of bright kernels compared to diffuse ribbons. So we have this degeneracy in stellar flares between the distribution of heating along the line of sight and in the XY plane.
Got it. Thank you. Do we have one last quick question? Shirley.
This is a question off a very different direction. We recently do a lot of machine learning, and then recently we were able to predict like frames of movies or frames from a self-driving car. You give them 4 frames, you predict the next 10 frames very nicely, even when the car's turning. So I'm curious, you've seen these movies of the sun rotating. I'm curious, people have been looking at, given the 10 years of observations of our sun, like from Soho or something, can you predict next week or next year, given we have so much data from before?
We cannot, in short answer. What we like to do is try to get a sense of the far side of the sun through helioseismic measurements, and therefore the active region distribution on the far side, because we want a much advanced notice of what's happening on the far side in terms of like new active regions emerging. Oftentimes, though, we will just find out about a new active region as it rotates around on the east limb of the sun. And we'll see that, new fluxes emerged, if that region was there previously, or the sunspots have gotten into a much more scary configuration. So it's really difficult to predict, say, 2 weeks ahead from now. New flux is always emerging in these active region nests and then dissipating, and it's just very difficult, but we try to get as much advanced notice as possible.